So this is sort of the mathematics of it, which was news to me. So if you consider the image processing we did earlier, we had 28 by 28 pixel images, so there were 784 pixel values. Had a camera shot. There were 784 pixel values, and so that means you're working in a 784 dimensional space. So high dimensionality is an issue. And so here is an interesting issue. If you take random points in a square, how many of those points are in the middle of the square and how many are near the edge? And if you try that at different dimensions, you get interesting, strange answers. So let's try this. This is just going to pick 1,000 random points using randomness here, and then it's going to count how many of those points are within 0.01, only 1% of the way in from an edge, and try it for various dimensionalities here. So for 2 dimensions, just a normal square, going to be the first one here. For 2 dimensions, only 25 of those points are on the edge. And for 3 dimensions, 29 out of 1,000 are on the edge. But when you go to high dimensional spaces, essentially every point is on the edge. And the reason is, if I'm in a 100 dimensional space, I now have to pick 100 random coordinates. And therefore, there's a pretty high probability that one of those 100 random coordinates will be below 0.01 or above 0.99. There are so many edges that the percentage of the space that is on an edge is very high. So that's one thing. You can't assume you're in the middle of this range. You are going to be always on the edge. That's one issue. And another thing is to consider the distance between random points in hypercubes. If you have a lot of parameters, because if you think about how you model things, you'll have if you go back to, say, let me bring back one of these early projects for an example, like this one. We had a curve here that we traced out with dots. There. If you want to trace out a curve like this, you could ask, how many dots do you need? Now, this is a lot of dots, but you can see if I want to trace out this shape, I need to have at least 10 points along that curve, and really maybe 20 points along that curve. So I need to have a sufficiently dense estimate. And so how much data would it take to trace out some kind of shape like this in higher dimensions? And the answer is really a lot. So if I copy this and go down here, and this is going to do, it's going to take 1,000 times, it's going to make 2 random points and just take the distance between them. It's going to show what the expected distance between 2 arbitrary points is. And so in 2 dimensions, the distance between 2 points is 0.5. But in higher dimensions, the distance between points gets larger and larger because there are more dimensions. So what this means is you cannot possibly have enough points to trace out the shape of the curve in a high dimensional space. It's absolutely impossible for 100 dimensions or 1,000 dimensions to ever have enough data to actually trace out the shape of the curve in all those dimensions. It would take an astronomical number of data points, which you can't possibly have. So for real machine learning, you must assume that you really don't have that many important dimensions. So if you have a 28 by 28 pixel image, there are 784 pixels, but not all of those pixels are really contributing independently to the answer. In fact, there's really only a small number of features that matter, which of course you could have told you in the first place. If I'm just trying to find handwritten digits and tell if it's a 0, 1, or 2, I really don't analyze every single pixel independently. I just look for, is there a closed loop? Is there a line? There really are maybe 10 descriptive features, combinations of pixels, that determine the answer. And all the rest of those 784 dimensions don't really matter. So that's the point here, and that's why you have this issue of dimensionality reduction. It is very common in machine learning that the input data has way too many dimensions. Consider a Tesla It's got a video camera in high resolution looking out the front, giving it a movie of all the images. It's got other receptors on it. You've got probably millions of data points coming in per second. So you could describe that as a million-dimensional space, but you can't possibly ever fit a curve through million-dimensional space. You have to reduce the dimensionality of it, and that's what we're going to do here. So the main way that's used, essentially the universal way that's used, is principal component analysis. What you do is you find out what combination of the input features captures the important part of the information. This, by the way, is how the human brain works. The human brain has the same problem. You look out at the world and you have all these photoreceptors in your eye. You're picking up thousands or millions of data points per second, and yet your brain doesn't have the computing capacity to deal with all that. So you have, I think it's the amygdala, you have a thing in your brain that performs an activity called attention, where it focuses on just the important part of all that data and throws away the rest. That's the only way you can get anything done. And your machine learning models have to do the same thing. You have to decide what the principal components are, what part of that, what combination of inputs contain the useful information, so I can ignore all the rest and get something done. So here, we're going to import these MNIST numbers again, these handwritten numbers from the census. So all this is going to do is input the numbers and put them in a 60,000 set for training and a 10,000 set for testing, as we've done before. So we got something to work with. And well, you'll see some of the numbers here. All right, so now we're going to decide how many dimensions to use. So we're going to find the number of dimensions needed to fit 95% of the variance. This is what principal component analysis does. It finds what combination of inputs captures most of the variance. And you can choose that I would like to explain 95% of the variance. So the original data has 784 independent pixels, so that's a 784 dimensional space. But if I use principal component analysis here and do a machine learning process to try different combinations and optimize it until I find the combinations that capture most of the variation, then I think we'll find here that it is something like 23 dimensions are all you need to capture 95% of the variation. Nope, 154. 154 to get 95%. Okay. Let's see. See, it's taking a while to fit. This is a machine learning task. Yep, it takes 154. So I had 784 dimensions, but I only need 154 of them to explain 95% of the variance. Now, what we can do here, this one here uses a random forest, which we talked about before, and it's only going to use 100 training images and 10 iterations to make it faster. It's going to find a good combination of hyperparameters for both of these. So it's going to use a random forest classifier, and it's going to reduce the dimensions, and it's going to optimize both of those activities. So it's going to try various values for the number of trees in the forest and for the number of dimensions to keep to try to find the most effective way to get the job done here. I missed the first letter in from. All right. And so it's going to try various values. A range from 50 to 500 and a range from 10 to 80. So it's going to try from 10 to 80 components, which are the combinations of features, and it's going to try between 50 and 500 trees in the forest. It's going to do a grid search through those parameters. So it'll take a little while, but it's not going to take very long. It's amazing how fast these Colab machines are and how simple these algorithms are. And so I'll just skip to the answer. When it's done, it determines that you only need 23 dimensions, 23 components, and 465 trees. So there are just 23 features, combinations of pixels, that are good enough to get the job done if you use 465 random forest trees. And so now you can see the result of this compression. you can reconstruct the images including only the 23 components instead of the original 784 components, so you can get a visual description of what you have done here. So here it is. Using only 23 components and 465 trees, it's able to get an accuracy of 85% at classifying them. And here's what the images look like when you keep only those 23 components. Now I'll just go to my answer here. So here's the original, and there's the compressed. So you can see you've done quite a bit of damage to these images, but you've kept enough to keep the main features. There's some sort of gray cloudiness and artifacts, but the important part is still there, the loop and the line. So this is enough information to perform the classification task, even though and therefore, of course, much faster and simpler. So this is called principal component analysis, and it is universally used to solve this amazing problem of way too much data, so it would be impossible to fit any curves through it, to iterate through it all, to have enough data or anything. Instead, you use principal component analysis to boil it down to a small number of dimensions that you can handle. And in retrospect, this is the only way you could possibly deal with the complexity of the real world. So that's what I wanted to show you, and there's some flags to find there.